Okay, hello everybody. Picking back up where we left off, I'm going to pick right back up on the PowerPoint with section 13.8. So I'm going to pick right back up with fluids in motion. Okay, so fluids in motion. So you have flow rate and you have continuity equation. Okay. One of the things that we're going to talk about first is the different types of fluid flow. If the flow of the fluid is smooth and relatively streamlined, it's called laminar flow. So laminar flow is shown by A. Laminar flow is also kind of a section of a creek that you know the water is moving, but the top is very smooth. So there's very little turbulence. Once the fluid starts moving at greater and greater speeds, it becomes more turbulent and it becomes turbulent flow. It has these little eddies, and think of a section of rapids, you know, from like a dam release if you've ever gone, whitewater rafting. So the viscosity of the fluid's much greater when eddies are present. So you have two types of flow. You have laminar flow and turbulent flow. Okay. If you deal with laminar flow, we deal with laminar flow most of the time. We talk about something called a mass flow rate. Okay. So mass flow rate is the mass of the fluid that passes a given point in some time interval. So it's a change in mass per time interval. So the flow rate at any 2 points must be equal, hence the term continuity equation. So if you want to determine the mass of something, okay, you take the density and you multiply it by its volume. If we have an area, okay, and you have a velocity, velocity is some distance per time, so it's some length per time. If that is length per time and you have a cross-sectional area, then you have some sort of cubic flow per time, or Q. If you have density at one point, area times velocity, it's going to be equal to the density, area, and velocity at some other point. So density at 1, area at 1, cross-sectional area of flow at 1, velocity at 1 is going to be equal to density 2, area 2, velocity 2. Now, a lot of times the densities are going to be the same, so this will simplify to A1 V1 is equal to A2 V2. I like this picture a little bit better. It kind of shows you if you have a pipe that is decreasing in area, right? If you have this cross-sectional area and velocity, this cross-sectional area and velocity is going to be equal to this between these 2 points. So if we reduce the area, you're going to increase the velocity. If you increase the area, you're going to reduce the velocity, okay? If the density doesn't change, typically you just have A1 V1 equal to A2 V2. Pipe is wider, flow is slower. Pipe is narrower, flow is faster. Velocity is faster, okay? So one of the examples they give is in the human body. If you have blood flow goes from the heart to aortas, which go into major arteries, gets smaller and smaller. Blood returns to the heart via the veins. The radius of the aorta is given as 1.2 centimeters. Blood passes through it at a speed of 40 centimeters per second. That's moving pretty fast. So a typical capillary, those are the tiniest things at the end of the system. Capillaries have a radius of 4 times 10 to the minus 4th centimeters. And blood flows through those at 5 times 10 to the minus 4th meters per second. Okay. They want us to estimate the number of capillaries that are in the body given this information. So I am going to share my whiteboard and density 2, velocity 2, area 2, density at 1, velocity 1, area at 1. So there's continuity equation. The densities drop out because the density is going to be the same. So you're just left with V2, A2, V1, A1. The cross-sectional area of the capillaries, okay, we need to multiply it by the number of capillaries, pi r squared. So this is my capillary side, is going to be equal to V1 pi r squared, and this is the aorta side. I'm interested in the number of capillaries times pi r squared for the capillaries. So what I'm going to do is solve this for n, which is V1 pi radius at the aorta squared, V2 pi radius squared at the capillaries. They gave us the velocity as 40 centimeters per second. So 40 centimeters per second is 0.40 meters per second. Coming over here, I see I have a pi in the numerator and the denominator, so those are going to cancel. The diameter of the aorta is 1.2 centimeters. So I'm using the velocities in meters per second and the diameters as centimeters. Now I can do this because the units are going to cancel. I just need to be consistent in the numerator and denominator with the velocities in meters per second and the diameters either in meters or centimeters. So the velocities need to match up and the areas, the radii need to match up. But I don't need to have meter per second and meters. You can to kind of keep things straight. But in this example, I'm going to keep the velocities as meter per second, which is 5 times 10 to the minus 4th. In the capillaries, this is at the aorta, but I converted this from centimeters to second to meters per second. Again, the areas, I'm leaving these as centimeters, so it's 4 times 10 to the minus 6th. Or I'm sorry, to the minus 4th centimeters. But that I'm squaring also. So the number of capillaries that I need is 7 times 10 to the 9th. So quite a lot. So there are quite a lot of capillaries in the body. So if we have a heating duct going into a room, what area must the heating duct have if air moving at 3 meters per second So we're given air moving at a particular velocity, 3 meters per second. Can it replenish the air? And it can replenish the air every 15 minutes in a room that has a volume of 300 cubic meters. Assume the air's density remains constant. Okay, well, that helps us because the densities will drop out. Okay, just be mindful on this one. We have velocities, which is lowercase v, and a volume, which is an uppercase V. I'm going to use the V with the line through it to indicate volume to kind of make this a little easier to follow. So what we have, we're given the time, okay, and we're given the time as 15 minutes. Well, 15 minutes is the equivalent of 900 seconds. Okay, because I'm given the velocity of the air is moving at 3 meters per second. So I want the units of time converted. So if I know A1, V1, density 1, A2, V2, density 2, but we were given that the density remains the same. They want us to, what area must the heating duct have? They want us to determine the area of the heating duct. So I'm going to say that's A1, which is going to be then equal to A2 V2 divided by V1. So we know that a velocity is some length per time. Okay, so if we look at this A2 V2 term in the numerator, the area, right, is some cross-sectional area, but the velocity is some length per time. Okay, so that's my A2 V2. So I'm saying this is length per time. Okay. If we have a volume, volume is given by some area, some cross-sectional area times a length. So if I have an area and a length, that's going to be my volume. Okay. So if I want an area, it's going to be some volume divided by some length. Okay. If I know that the area is a volume per length, so now if I take this and plug it back in, I have some volume per length. So this A is this A. And then my velocity, I have some length per time. These lengths will cancel, which is the length of the room. So I'm left with volume per time. So area is volume per length, volume divided by length, and velocity is length per time. The lengths cancel out. So A2 then becomes, or I should say A2V2 becomes volume per time. So now this term up here, I have A1. A2 is now the volume per time of the room, or the volume per time, which is A2V2. So A1 is now volume per time, which is this A2V2 times V1. So the volume of the room was given to us as 300 cubic meters. The time that we want the air to replenish is the 900 seconds, or 15 minutes. And the velocity they gave us as 3 meters per second. So the cross-sectional area of the vent is 0.11 meters squared. Okay. So let's talk about Bernoulli's equation and Bernoulli's principle. So where the velocity of a fluid is high, pressure is low. Where velocity is low, pressure is high. So it makes sense as force is required to accelerate the fluid to a higher velocity. So what we have then is if you consider a fluid, if you look at the work it takes to move some very small volume of fluid from one point to another while it is in laminar flow. So this isn't turbulent flow. The turbulent flow is a completely different thing, and you will deal with that when you get to an actual fluids class where you spend an entire semester talking about this. You'll look at Moody diagrams, and but for now, we're just dealing with laminar flow, which is where we use Bernoulli's equation. So work must be done to accelerate the fluid and increase its height. So you have conservation of energy is used to derive this equation here. So P1, so at some location 1 and at some location 2, you have pressure, okay? You have velocity, 1/2. So this is kinetic energy, this is pressure, and this is elevation. So this is potential energy, kinetic energy, pressure. Like I said in the first video, when you do pump design, pumps are designed based on head or elevation that it can push, okay? In Bernoulli's equation, in some forms of engineering, they call this pressure head, velocity head, and elevation head, okay? Like I said, particularly in pump design. So if we're looking at flow through a heating system in a house, okay, we'll say that water circulates through the whole house, the hot water heater system. If the water is pumped at a speed of 0.5 meter per second through a 4-centimeter pipe in the basement under a pressure of 3 atmospheres, they want us to determine what will the flow speed and pressure be in a 2.6 centimeter pipe on the second floor that is 5 meters above the same location. So assume the pipe does not divide into branches. Well, there's probably a few too many unknowns for us to jump right into Bernoulli's equation, but there aren't too many unknowns for us to, so the first part of this, part A, they want us to determine flow speed and pressure of the pipe on the second floor. Okay. So Bernoulli's equation, too many unknowns. The density is going to be the same. So I'm going to simplify continuity equation right out of the gate and drop the densities and say A1 V1 is equal to A2 V2. Okay. So I want to determine the second velocity, which I don't know. V1A1 divided by another, the other cross-sectional area. So areas, they're circular pipes. So V1, so it would be pi R1 squared over pi R2 squared. Pretty much at any time you can cancel the pi's out. That would be up to you, or you can carry them through. In the basement, we're given that the velocity is 0.5 meter per second. We're given that the diameter in the basement, it's a 2 centimeter pipe. So for area for a circle, you can do pi r squared, or you can do pi d squared over 4. It's up to you. I'm doing this one. We were given a diameter in the basement of 4 centimeters. The radius is going to be 0.02 meters. So be careful with that and be careful with what you're given. Okay. The other radius on the second floor is a 2.6 centimeter pipe, which would be 1.3 centimeter radius if it's a 2.6 centimeter diameter. If I convert that to meters, I end up with 0.013 meters. So just be careful on a test. If I give you pipe diameters instead of radii, you need to know how to convert that. So then V2 is going to be 1.2 meters per second. And based on everything we've seen so far, this makes sense. If you have a 4 centimeter pipe traveling at 0.5 meter per second, if we reduce that pipe size from 4 centimeters in diameter to 2.6 centimeters in diameter, I've increased the velocity up to 1.2 meters per second. So that's the first part of this problem. Now that I have those things, I can take a look at Bernoulli. So this is continuity equation. Now let's take a look at Bernoulli's equation. P1 1/2 V1 squared plus GY1 is equal to P2 plus 1/2 V2 squared plus density GY2. We are given in the basement that the pressure is 3 atmospheres, but we need to use newtons per meter squared. We need to convert the atmospheres from 3 atmospheres to 3 times 10 to the 5th Newton per meter squared. So if I want to solve for P2, and I know P1, okay, P2 is going to be equal to P1 plus, now I'm going to combine these terms, and I'm going to factor out a density gravity. Y1 minus Y2. At any point in time here, you could plug the numbers in up here. You could plug your 3 atmospheres in, 1/2. We'll know the density of water. We know the first velocity. We know, again, we know the density. We know gravity. We know the elevation difference between the two. So you can plug the numbers in here. I am just rearranging and moving things around to solve for the pressure here. You do not need to solve it this way. If you want to solve it by plugging the numbers right into the straight up Bernoulli's equation, you should get exactly the same answer, right? So P2 is going to be our 3 times 10 to the 5th Newton per meter squared. There's P1. Density of water, 1.0 times 10 to the 3rd kilogram meter cubed times 9.8 meters per second squared. So there's my gravity. Y2 minus, or Y1 minus Y2. I am -5 meters, right? Because I'm Y1 minus Y2. So if I'm 0 minus 5, because Y2 is the upper floor, hence the -5, plus 1/2. So now I'm on to the velocity component of this. 1.0 times 10 to the 3rd kilogram per meter squared. V2, or I'm sorry, V1, which is in the basement, 0.5 meters per second. This is squared, minus, from part A, we determine the 1.2 meters per second. That's squared. Right? So this works out to 3 times 10 to the 5th Newton per meter squared minus 4.9 times 10 to the 4th Newton per meter squared minus 6 times 10 squared Newton per meter squared. So we got 10 to the 5th, 10 to the 4th, 10 to the 2nd. So this works out to 2.5 times 10 to the 5th Newton per meter squared, or roughly 2.5 atmospheres. And again, the pressure in the basement is 3. Pressure on the second floor where the pipe comes out is 2.5. Okay. So that's using a combination of both continuity and Bernoulli. So for applications of Bernoulli's principle, so you have airplanes, baseballs are the two most common. If you have a closed container like a vat and you have a spigot on the end of it, and you have your velocity up here is 0 and you have a velocity down here, okay, so the velocity is not moving across. It might be going down, but it's not moving across. And you have an elevation difference. You can reduce Bernoulli's principle to this, which is called Torricelli's theorem. The velocity at this spigot is being driven by the head that's above it. So the greater the head, the more water that's above this spigot, the faster the velocity is coming out of it. So how do airplanes work? Airplanes work because of the shape of the wing. An airplane wing has a longer length on the top, so air traveling over the top of it has to go a further distance than air going under it. Okay, so it has to go at a higher velocity, hence a lower pressure. So higher velocity, lower pressure. So it's due to the different airspeeds and pressures on these two surfaces. Going under it, it's a shorter distance, slower speed, higher pressure. If you have lower pressure on the top, higher pressure on the bottom, you generate something called lift. So the airplane essentially the airplane flies. In racing, in Formula One, those cars have wings, but they're turned the exact opposite of these wings. So instead of creating lift, they're creating downforce, pushing the car into the ground so that the car can go faster around a turn because it's being pushed down as it goes. Sailboat can move against the wind using pressure differences on the side of the sails and using the keel to keep it from going sideways and still steering it, okay? Baseballs, when pitchers throw the baseball, they put a spin or a curve on the ball. That spinning is what is causing the ball to behave some of the way it does, okay, because of those pressure differentials. A person with constricted arteries may experience something called TIA, which is temporary lack of blood flow to the brain. Again, this is caused by differences in pressure. Another way to measure pressure differentials is using Venturi meters. So you can set a pressure gauge at one spot and a pressure gauge at another spot. And what you're doing is you're measuring these pressure differentials in an object called a Venturi meter. Okay, so from this, okay, from this point forward, none of this material is going to be on the test from this point going forward. Okay. It's all stuff that is asterisk sections in the chapter. Some of the stuff's pretty interesting. I'm going to go over it very briefly. Before I go on, okay, if you take velocity, right, and area and multiply them together, you have area, which is, you know, some length squared, and you have velocity, which is length per time. If you multiply V1 and A1 together, okay, you end up with cubic units of something per time. That's the mass flow rate I was talking about earlier. In fluids, in civil engineering, we call that Q, uppercase Q, or flow rate per time. You're talking about cubic meters per second or cubic feet per second of fluid flow per time. Okay. Viscosity. Viscosity is an internal friction in real fluids. Okay. So the viscosity can be measured if you have a stationary plate and a moving plate based on the equation that you see there on your screen. So the internal friction in a fluid is called its viscosity. Okay. Rate of flow in a fluid in a round tube is going to depend on viscosity, pressure difference, and the dimension of the tube itself. The volume flow rate or mass flow rate is going to be proportional to the pressure difference. It's also going to be inversely proportional to how long the tube is and to that same pressure difference. It has consequences for blood flow, but basically in the textbook, they have an equation for this. Q is equal to pi r to the fourth, change in pressure divided by 8, and then a constant divided by length. That's this Poiseuille's equation. You're not responsible for it. You're not going to be tested for it. But that equation is why it has consequences for artery and heart flow. You'll see that pressure builds by a factor of 4. You're increasing it by an exponential of 4. Okay, so surface tension and capillarity. So some of the weird things you see in nature, like this beads of liquid on like a blade of grass, are caused by surface tension. The reason they work, the reason they happen, is due to surface tension and capillarity. So surfaces of a liquid at rest are not perfectly flat. They either curve upward or downward to follow the wall of whatever it is that it's holding on to. So this is called surface tension, and it makes for some interesting elastic behaviors, like you see with the beads of water on a blade of grass, or like you see in a bubble wand. You know, that ability to hold on to the edges of that circle has to do with surface tension. Okay. Water striders. The reason that a water strider doesn't sink is because it's such a small surface area, but there is some surface tension in the water that they're not poking through the surface of the water. So different types of fluids are either attract water or they repel water. So soaps and detergents have lower surface tensions, and it allows water to penetrate materials more easily. So water molecules are more strongly attracted to glass than they are each other. So in that case, water wants to crawl up the surface of a glass container. That leads you to that meniscus shape that you read the bottom of the meniscus in chemistry classes. that leads to that curved shape. That has to do with surface tension and capillarity. As opposed to mercury, it's the exact opposite. They're not attracted to the surface of the glass, so it dips downward. So it's like the meniscus is upside down. Okay. If you have a tube that's narrow enough that you place it down into a fluid, the fluid will work its way up the tube, you know, and that is what capillarity is. So pumps and hearts work on fluid principles. Okay, so you can have a simple intake and outtake for a reciprocating pump. Your heart is a pump. This pump intended to move water is called a centrifugal pump, as it spins in a circular motion. Again, human heart is a pump. So to summarize chapter 13, there's 3 main phases of matter that we talk about: solid, liquids, and gases. Again, yes, plasma is a thing, but for the purposes of this, we're not really going to discuss it. Liquids and gases are called fluids. Density is a mass per unit volume. Specific gravity is ratio of the density of some material to that of water. Pressure is a force per unit area. Like I said, I like to think of pressure in terms of tire pressure, so PSI, pounds per square inch. Pressure at a depth, usually in water, H is given by the density of water, GH. External pressure applied to a confined fluid is transmitted throughout that fluid. Pascal, right? Atmospheric pressure is measured with a barometer. Gauge pressure is the total pressure minus atmospheric pressure. I prefer to think of this as total is equal to gauge pressure plus atmospheric pressure. An object submerged, either a whole thing or partly in fluid, is lifted upward by a buoyant force, which is equal to the weight of the fluid that the object displaces. Archimedes principle. Fluid flow can be laminar or turbulent, and the product of cross-sectional area of flow and speed is constant for horizontal flow. That's your mass flow rate. If you take cross-sectional area times velocity, you end up with cubic units of fluid per time, Q, mass flow rate. Where the velocity of a fluid is high, pressure is low, and vice versa. Viscosity is internal friction force within the fluid, and liquid surfaces hold together as if they are under tension. So like I said, you know, some things tend to, you know, attract, and some things tend to repel. Hydrophobic versus hydrolyphic, I think. Hydrophilic. We talked a little bit about soaps and oils. Soaps tend to break down oils. The fancy word for soaps are surfactants. They break down, they reduce the surface tension to be able to break the oil up. Again, those last 4 items, those are not going to be on the test. I just think it's some interesting stuff that if you're going for a degree in engineering, you're going to be talking about some of this stuff. So if you have any questions, bring them to the next Zoom meetings, or shoot either Professor Miller or I an email, and would be happy to get back to you. There is going to be a split now in the chapters, right? So we're stopping here at the end of chapter 13. The next one that we're going to pick up on is chapter 17. We are skipping chapters 14, 15, and 16. Those will not be on the test at all. The next chapter we're going to pick up on is chapter 17. So with that, we'll see you when we do chapter 17. And please keep in touch with us with any comments or questions. Have a great day.